Hello everyone, how's it going? My name is Dan the Tutor, on a quest to become the world's greatest tutor. In today's video, we're going to be talking about Avogadro's number. So Avogadro's number is a constant used in chemistry, and I'll just tell you the number. It's 6.02 times 10 to the 23rd power. And there you go, that's the end of this video. Thank you all for watching. But no, when do we use this number? How can this number be used, and why is it so important? Well, I'll tell you. You may have heard of the mole before. Not the mole, the animal, but a mole in chemistry, one of the fundamental units that we use all the time in this class. And you may have been wondering for a while, or maybe you've never even heard of this before, but what is a mole? Why is it important? I'll tell you why. And it has to do with Avogadro's number. So basically, 1 mole, MOL, which is the abbreviation of mole, it's like how we write JUL for July. You know, we really save some time by getting rid of the Y for the abbreviation. So 1 mole, MOL, is the same as 1 mole, MOLE, is equal to Avogadro's number, 6.02 times 10 to the 23rd power, molecules or atoms. And the reason why I say molecules or atoms is because if it's a compound, such as water, H2O, then it's a molecule, or if it's individual atoms, like for instance just hydrogen or oxygen or whatever, then the units are atoms. Even something like H2, for instance, is technically a molecule because there's more than one atom there. It's H2. But that's getting into the nitty-gritty. Really, I just want you to know 1 mole is 6.02 times 10 to the 23rd molecules or atoms. And so now let's look at some examples of how we can use Avogadro's number to answer some basic questions. Let's say I have 1 million atoms of iron, Fe, and I want to know how many moles is that? Well, let's find out. 1 million is, a big number. It's probably a lot of moles. Well, all I have to do is I'm going to write 1 million atoms times the conversion factor, which is Avogadro's number, 6.02 times 10 to the 23rd. The reason why it's in the denominator is because that's where the atoms go, which is going to cancel with that atoms right there. And in the numerator, I will have 1 mole. So there's my conversion factor. It looks like I am going to be dividing. And if I plug that in my calculator, I get 1.17 times 10 to the minus 12th moles. And that is going to be our answer. By the way, this is an extremely small number. So when I said it's going to be a lot of moles earlier, that was a joke. As a matter of fact, this number is so small, it's equal to 0.000000000000117. And that's how many moles are in a million atoms of iron. So I think you'd agree, pretty small. Now, before we do the next practice problem, we just need to quickly refresh yourself on molar mass, which is the way we convert between grams or mass of a substance to the number of moles in that substance. And the reason why I'm telling you to review that is because problem 2, let's say I start with 15.0 grams of sodium, Na, and I want to know how many atoms is that. So if you forget how to use molar mass to turn grams into moles, I have a video on that. You can look at the description and watch it. Or if you already know, go ahead, pause the video, see if you can solve this one on your own now. Okay, and here's the solution. So I start off by saying 15.0 grams of sodium, and I have to convert that to moles. So in this case, I'm dividing by the molar mass, because that will get me grams to cancel out and moles in the numerator. So referring to my periodic table, sodium has a molar mass of 22.99 grams in 1 mole of that substance. And that will get me 0.652 moles of sodium. But if I want to know how many atoms, then I have to use this number, 0.652. And technically I'm using all the digits in my calculator. So 0.6524575,903. And the reason why I'm doing this is I don't want a rounding error, and I don't round to sig figs until the last step, the final answer. So anyways, it's this many moles times Avogadro's number, This time I have 1 mole in the denominator to cancel out moles there, and 6.02 times 10 to the 23rd atoms will therefore go in the numerator. And when I plug that in my calculator and round to 3 sig figs, which is how many sig figs I need for this one, I get 3.93 times 10 to the 23rd atoms. And that is my final answer. So as you can tell, that is a lot of atoms, more atoms than you will ever be able to count in your lifetime, even if that was your full-time job and you never took an hour of sleep. So it's a lot. And now we're just going to do one more problem, very similar to the last one. I want to know how many molecules are in 6.1 grams of H2O. So again, you can pause the video, give it a try on your own, and when you're ready to see the solution, unpause. Okay, so first I'm doing 6.1 grams of H2O times, or really divided by, the molar mass, because grams goes in the denominator and moles in the numerator. So, molar mass of H2O, hydrogen is 1.008 molar mass, times 2, because there's 2 hydrogen, plus oxygen, which is 15.999. That's going to give me a total molar mass of 18.015. That is what goes in the denominator down here. 1 mole always in the numerator. And it looks like I get 0.3386 moles of water, which again, I take this number, 0.3386 moles, and I'm going to multiply by Avogadro's number, 1 mole in the denominator, and 6.02 times 10 to the 23rd molecules in the numerator. So then I plug that in my calculator, and rounding to 2 sig figs this time, because I only had 6.1 grams of water, which is 2 sig figs, I get 2.0 times 10 to the 23rd, and this is now molecules of water, and that is going to be my answer. So hopefully that makes sense. If you do have any questions, please post them in the comments. Have a wonderful rest of your day, and I'll see you in the next video. Take care, and bye-bye.